This next section of the presentation is another look at the relationship between the inputs, outputs, I/O modules, the backplane, and the processor's data table. It will be brief compared to earlier presentations, but still complete in its scope. If you are already familiar with the active backplane concepts, this next section makes an excellent refresher for you, with completely new graphics that you haven't seen in earlier presentations. Here we have rearranged the components, but I am sure that you recognize this circuit. From right to left, first you have several conductors of the backplane data bus in blue, a connector between the backplane and the I/O module, and the output circuitry of a single point of DC output. The circuitry of a single point of output includes the backplane gate circuit, which connects this circuit to the backplane or disconnects this circuit from the backplane by way of a signal from the processor. A holding circuit, which maintains the last state sent from the processor by way of the backplane. The opto-isolator that isolates the field power source from the I/O module's power supply, and then the output device itself. In this case, a solenoid. In an actual output module, there would be additional circuit between the opto-isolator and the output terminals in order to interface the opto-isolator to the higher current levels needed for the actual output of the solenoid. When the processor is in the run mode, it cycles through the collection of input image, collects all the input data, the program scan of the logic, the transfer of the output images out to each output module, and then the communications with external devices such as your laptop or an operator interface terminal. During the output image transfer, the 16-bit words are placed on the data bus of the backplane one word at a time. Here we show three of 16 of those lines on the backplane, and we show one line as having a high signal on it, but notice the signal is blocked at the backplane gate circuit. The high and low status of each of the 16 bits is felt at the connector of all of the I/O modules on the backplane. The backplane gate circuit controls whether or not this output point actually receives the update from the processor. If this card has been selected to be activated by the executive program in the processor, a signal will enable the backplane gate, and the high or low state on the data bus of the backplane will be felt by the holding circuit for that I/O point. The holding circuit controls the actual output circuitry and holds the output on or holds the output off until the next output image scan. Again, this is one of 16 outputs of an I/O module. Here we have all 16 output circuits represented with the backplane data bus and control bus. The processor puts the data on the backplane, but is not seen by any of the modules until the module is actually activated by a slot decoder. So until a slot decoder is activated, none of the modules on the backplane see the signal. The slot decoder senses the signal on the control bus and activates or deactivates this module at the processor's request. Each slot has a decoder that is unique to that slot, in that it responds to a bit pattern sent from the processor on the control bus that corresponds to that slot and that slot alone. When this happens, the output of the slot decoder activates all 16 gate circuits, and the state of all 16 backplane conductors of the data bus are felt at the holding circuit of all 16 output circuits. That is the sequence of an output signal from the processor. During the input image scan, the process is slightly different, but basically the same. The input image scan, the processor activates the slot of an input module resident in that slot, which allows a state of all 16 input devices to be felt on the backplane 16 conductors on the data bus. The processor then reads the 16 states from the data bus into a word in memory assigned to that slot. That is all there is to the activity of I/O modules on the backplane. Let's look at the backplane. Looking at a more complete section of the backplane, let's say for a 4-slot chassis, but keeping the illustration simple with just 16 conductors for the database. The power, the common, and the control bus. And of course, we need a power supply. The power supply supplies all the power for the I/O modules internally, but it does not supply power for the actual devices connected to the I/O modules in the field. Even if the PLC power supply has a surplus of power and a means to connect to your field devices, to connect them to the PLC power supply, it is not good practice. If a short occurs in the field wiring, and the fuse blows in the power supply, you have disabled the PLC as well. To the backplane, add the edge connectors to accommodate the processor in slot 0 and the lesser I/O modules in slots 1 through 3. Notice the processor modules connector encompasses the control bus, whereas the I/O modules do not, because the control bus signals the decoder, which is part of the backplane, and then the decoder feeds through the module connector to activate each module. Between the control bus and each I/O slot connector, we add a decoder. The decoder will respond to the slot number at each of the corresponding slots. Let's remove the power supply from our limited screen space. The chassis is ready to accept I/O modules, starting with the processor module. For the sake of simplicity, we are limiting the components of the processor module in this diagram just to those that we need for this discussion. The two primary connections of interest to us are the data bus in green and the control bus in red. Now, by means of the I/O controller, the CPU sends an encoded binary signal down the length of the control bus to affect a slot decoder to activate the slot of interest to the processor. The data bus is connected to the memory array, and the processor can select a word in memory by means of the memory controller, as well as read data from the memory into the processor by way of the memory bus. The memory bus is 16 bits as well, but we have abbreviated it to one line to save space in this diagram. Although the memory of the processor has no structure when first encountered, that is, before you have created a project and downloaded a program into the PLC's memory, I have divided up the memory into 3 groups for the sake of demonstration: I/O data, user configured data table, and program files. To our PLC system, let's add a 16-point output module represented by a single point of 16 points. Remember from a previous discussion that the backplane gate circuit switches the state from the backplane conductor to the holding circuit, which controls the actual output. To our PLC system, let's add a 16-point input module represented by a single point of the 16 points. Remember from a previous discussion that the backplane gate circuit switches the state from the actual input device to the backplane conductor. You may also remember from a previous discussion that when the processor is in the run mode, it continuously steps through a sequence. First, scanning the backplane by activating input modules one at a time and storing the input images in words of memory associated with each slot that was configured with an input module. Secondly, executing the rungs of logic against the data stored in the data tables, and then scanning the backplane by activating output modules one at a time and transferring the output images from the words in memory associated with each slot that was configured as an output module. Let's examine this sequence in more detail. During the input scan, the processor activates the input modules in numerical sequence. We only have one card in slot 3. The processor sends a signal across the control bus, and the decoder at slot 3 reacts, enabling the backplane gate circuits of all 16 inputs connected to the module in slot 3. And whatever the state of the inputs are in, this is felt at the memory array in the processor by way of the backplane. Logically, since the processor knows which slot it activated, it knows which word in memory to gate the 16 states from the backplane into that word in memory. So the memory controller activates a word, and the information from those 16 bits is then stored in that word. The input image from the input module in slot 3 is now stored in memory variable I:3.0 for use by the program logic in the next step of the sequence. A quick review of the memory layout before we execute program final ladder 2. The memory is divided into 3 primary sections: I/O data files, user configured data files, and the program files. Ladder 2 of which is automatically executed when the processor is in the run mode. Now we are ready to execute a rung of logic. First, the processor retrieves a rung of logic from ladder 2 in memory by activating the memory location where the rung is stored. For this demonstration, we have a simple rung. After the rung is retrieved, the processor begins by executing this rung of logic. First, by reading the state of the memory location that the first instruction is addressing. Then the processor solves the first instruction against the state of the memory location that the instruction was addressing. The instruction, an XIC, which stands for examine if closed instruction, is more properly referred to as a true if on instruction. This instruction is true if I:3.0/3 is on. If the bit as memory location is off, then this instruction is false. If the bit is on, then the instruction is true. We will assume that the bit was on when the input module was scanned and highlighted as true. The logic is solved from left to right. So the processor looks at the next instruction. It is a write instruction, not a read instruction. So instead of reading the state of the memory location that this instruction is addressing, we will write to the state of that memory location with the state of the logical rung. So the rung is true. We are going to write a 1 to memory location O:2/7. First, by activating that word by way of the memory controller, and then by sending the state of the bit to that bit in memory. Now, when you look at this diagram, you see now that both the true if on instruction, the read instruction, is highlighted, and the energize output instruction is also highlighted. These highlights don't mean the same thing. If it is a read instruction, then it is highlighted if it is true. It is not highlighted if it is false. So all of the read instructions are highlighted based on true or false. The output instructions, however, are highlighted based on or off in memory. So you could say that the OTE instruction, the energize output instruction, if that bit is on in memory, then it will highlight that instruction. Whereas the true if on is highlighted because the instruction is true. keep in mind, if that was a true if off instruction and the bit was on, it would not be highlighted. So you see there's a difference between what is highlighted in the read instructions, the permissives or conditions in the rung, and what is highlighted in the output instructions. Let's recap real quick here. The processor scanned in the input image from the input module into the processor's memory. The processor scanned the program file of one rung, solving the instructions and writing the results to the processor's memory. The next step is to transfer the output image out to the output module. The output image word I:20 is activated onto the backplane and felt at the connector and backplane gate circuit on all of the modules on the backplane. But only one module is activated by means of a binary signal on the control bus. All 16 backplane gate circuits are activated simultaneously of that one module, and the output image is felt at the holding circuits of all 16 outputs, and the output devices are switched on or switched off to match the output image transferred out from the memory location O:2.0 that was transferred out to the output module in slot number 2.